Welcome back. To truly master the asset management, you have to move beyond just fixing what's broken. You have to become a student of why things fail in the first place. In the asset intelligence framework, we don't settle for superficial answers. We look for the technical truth. Every failure you encounter falls into one of two categories: natural deterioration or forced deterioration. Natural deterioration is the inevitable cost of operation, the predictable wear of a component over its rated life. But forced deterioration is what kills your plant's performance. It's when an asset fails prematurely because of environmental stress, poor operating conditions, or systemic neglect. Today, we are diving into root cause physics. We are going to look at the fundamental laws of science to identify which type of deterioration is eating your ROI and how to stop it permanently. To solve a problem, you must first respect physics. Natural deterioration is a planned event. We use data, bear rates, and historical intelligence to predict it and schedule an intervention before a failure occurs. This is clean maintenance. But forced deterioration is the enemy. It is the leading cause of the unplanned stops and firefighting that plague most facilities. In an AIF investigation, we start with the physical evidence. If a motor burns out, we analyze the windings. Was it a natural insulation breakdown at the end of its 50,000 hour life? Or was the insulation forced to fail because the cooling fans were clogged, or the voltage was inconsistent? Physics doesn't lie. If the applied stress, be it heat, friction, or vibration, exceeds the material's structural limit, the asset will fail. Our job is to determine if that stress was a natural part of the process or a forced condition we failed to control. Once the physics of the failure are clear, we have to look for the systemic gap. If an asset suffered forced deterioration due to a missed lubrication cycle, we don't ask for more training. Training doesn't change the physics of a dry bearing. Instead, we ask, why did our system allow this asset to run to the point of failure? We use the AIF hierarchy of controls to build a permanent solution. Level 1, design out. Can we eliminate the failure mode entirely? Example, replacing a lubricated bearing with a sealed for life unit or a magnetic coupling. Level 2, early detection. Can we install an intelligence layer that flags the start of a forced deterioration, like a vibration sensor that alerts the team weeks before a seizure occurs? Level 3, standardized process. If a manual task is required, how do we error-proof the system so that the machine simply cannot be operated in a way that forces its own destruction? We want solutions that work in the real world, where conditions are harsh and schedules are tight. We solve the physics so the human factor becomes a non-issue. A core pillar of the asset intelligence framework is using historical intelligence. We shouldn't be starting our investigation after the smoke appears. We should be looking back through the SCADA and CMMS data for microsignals. Most forced deterioration leaves a digital trail long before the physical break. It shows up as a subtle rise in current drop, a slight drop in pressure, or an abnormal thermal signature. In a mature AIF environment, we treat this signal drift as the root cause itself. By identifying the physics of the drift while the machine is still running, you transform a potential catastrophe into a controlled 15-minute adjustment. That is the essence of proactive intelligence. Let's look at a model scenario. A chemical processing plant was replacing a mechanical seal on a high-pressure pump every 3 months. The initial reports blamed installation quality. We applied root cause physics. We analyzed the piping geometry and the flow data. We found that during every batch startup, the pump was experiencing cavitation. Tiny vapor bubbles were collapsing with enough force to pit the metal. The physics? The intake pipe was undersized for the flow rate required by the new production targets. The deterioration wasn't human error, it was forced deterioration caused by a system design that was being pushed past its physical limit. Each seal cost $5,000 plus 6 hours of downtime. The total annual loss was $120,000. The fix? We upsized the intake pipe for $12,000. The seals now last for 3 years. We removed the first element by aligning the system's physics with the process's demands. The error vanished because the machine was finally allowed to run within its natural limits. Your homework for today. Take the bad actor asset in your facility, the one that breaks once a month. Ask yourself, is this failing because of natural wear, or is there a force in our environment forcing it to fail prematurely? Find that force and you'll find your solution. In Module 6, we are going to take this investigative mindset and apply it to the 9 types of waste. We are going to find the friction in your entire operation, the forced deterioration of your time and money, and remove it. I'll see you there.